Welcome back to the GHGCast, a window into the world of a Canadian company with a big idea to become the global reference for greenhouse gas emissions in the interest of reducing them. I'm Alexander Milas, and for this quick cast, we virtually sat down with someone who's all about maintaining a bird's eye view of emissions. He's the manager of Airborne Systems at GHGSat, and he joins us from their headquarters in Calgary. Welcome, Warren Shaw. Hello, Warren. Thanks so much for joining us today. And so tell us, in the end of 2019, you launched a different sort of device, the company's first aircraft center. Now, what was your role in all of that? And tell us a little bit about your background. What is it precisely that you do as a manager of Airborne Systems at GHGSat?
Well, my background's sort of a physics and astrophysics background and by education, but as far as work experience, I had over 10 years experience in airborne hyperspectral imaging and thermal imaging. So that's kind of how I got connected into GHGSat when, the idea was to take that same kind of satellite technology and put it onto an aircraft platform. So that's kind of why I joined early 2018, and yeah, like you said, late 2019 we had sort of our first launch with our airborne platform to sort of manage, monitor, and detect emissions from a different platform than the satellite.
So how do you prepare for something like that? And I guess going back before even that, what was the need for it all? What was the actual spark that brought this kind of very innovative kind of technology about them?
Yeah, it's really interesting. I mean, the idea to have the airborne platform actually came from our customer base. So as we were talking to some of our partners and customers, related to the satellite technology, they were saying, "Hey, this is great, but we see a need for perhaps another tool in our toolbox to be able to monitor our emissions, and bringing it from 500 kilometers up with the satellite down to that aircraft level. It gives you a different picture of the ground, gives you a different picture of the facilities that could be potentially leaking." And so it was really some interest from that community that set us on this path to taking that satellite technology. It's at the heart of it, it's the same kind of spectrometer system, but sort of packaging it in a way that could be installed in a fixed wing airplane to do the surveys from an aircraft altitude.
Well, we were talking a little bit about Iris, but of course, I suppose every launch carries with it a lot of emotion. So tell us about that first flight, the launch of GHGSat AV1.
Yeah, so AV1, I mean, just so aircraft variant is kind of what the AV stands for, and that's really what it is. It's a variation of what we did with the satellite to put into an aircraft platform. And our first flight, our first light flight was December of 2019. So I definitely had a lot of emotions. I definitely felt the cold as well. It was a pretty cold day for that first flight, but we got airborne. The system worked really well, which was obviously all really great. And we were able to collect some data, put it through its paces, and really sort of kick the tires on this new system and get that first kind of look at the ground. And obviously after the flight was sort of the follow on the processing and digging into the data and seeing if there's things that we could optimize. But yeah, it's definitely really exciting, really rewarding to see all the hard work over the couple of years leading up to that, and all the efforts of the team coming together and sort of, realizing that, with that flight was great.
Well, no kidding. I mean, I suppose, GHGSat is about satellites. The clue is in the name, right? So how did you adapt that satellite technology for aircraft?
Right. Yeah. So, I mean, like I said, at the heart of it, it's still the same kind of fundamental imaging spectrometer system based on our patented Fabry-Perot system. So, the light comes in and you have a two-dimensional imaging array. And so you have the two spatial dimensions, but kind of imprinted on that is that spectral information. So we're looking at a very narrow spectral band. That's obviously where methane will absorb the solar illumination on the ground. And so as we image, the strength of that absorption feature then is proportional to the abundance of methane in your field of view. So at the heart of it, it's using all that same kind of technology. And so as you have that two-dimensional image of the ground and the forward motion of the satellite or the forward motion of the plane, you can image the same ground point at different points on the detector, which in turn is sampling that ground point at different wavelengths, and you can build up that hyperspectral data cube. So that's the system. What's neat about it is the idea that, okay, well, we want to put it into quite a different environment. So satellites, it's great. You launch this thing and you've got that crazy several minutes of a lot of vibration G forces. But once you get to space, it's a nice smooth ride for your imaging. On the aircraft side of things, we don't have to survive a launch, those types of conditions, but the actual conditions that we're imaging in as we're flying along, you're going to be dealing with things like turbulence, and you're going to be dealing with winds or other factors, temperature changes, things like that. So we definitely had to kind of keep the core technology there, but put it in a system that could handle the aircraft environment. And so things that we're doing, we're including some, vibration damping. We're including some gyro stabilization to compensate for the aircraft motion, things like that. So, yeah.
So what is gyro stabilization exactly?
Basically, what we're trying to do with gyro stabilization is as the plane's flying along, its attitude, its roll and pitch and yaw and all that is changing. And so gyro stabilization, what it does is it using gyros, and it can even be more elaborate using an actual IMU kind of GNS system that actually kind of senses where the plane is at any given instant, and then it sort of compensates for that. So as the plane is rolling and pitching and yawing, the gyro stabilization system is compensating for that, so it keeps your camera as smooth and as steady as possible as you're flying down your flight line. So what's great about that is it allows you to keep nice straight flight lines as you're going down and not kind of wobbling all over. But it also means that you don't have to have as much side lap between the flight lines because your camera's staying nice and nadir, meaning looking straight down as it flies along. And so without that gyro stabilization, you might have to sort of overlap your flight lines a little bit more to make sure you don't miss anything on the ground. But by having that, you can be more confident that you're seeing everything along there, and you can space your lines out a little bit more, which of course means that you get to have more coverage of an area to be able to cover more at a lower cost for our customers.
Yeah, well, I mean, I suppose it's all about having a different view, a different perspective. So tell us about what you can see that you can't actually see from orbit. What are the advantages of doing all this?
Yeah, of course. So again, 500 kilometers up, and our nominal kind of flying altitude would be about 3 kilometers up. So obviously, we're a lot closer to the ground, and that gives us some great advantages. Certainly, the spatial resolution. So a pixel on the satellite that might be 25 kilometers coverage. Our pixel coverage, our spatial resolution at a nominal altitude is getting down to less than 1 meter. So we have a much finer spatial look at all the different facilities and assets that we're flying over. So we have that ability to resolve the location of any emissions detected more finely. So rather than just getting it to perhaps the same pad or the same facility, we could potentially resolve it down to a certain piece of infrastructure on that facility, something like that. So there's definitely spatial resolution advantages to going lower. And combined with that, there's a detection threshold advantage as well. So because we're closer to the ground, the signals that we see, the shape of the plume is going to be more well resolved. And so we'll be able to actually see smaller emissions, things that will be kind of lost among the background from a space. We actually have that pixel resolution to see it. And so we can actually see smaller leaks. And so we have a detection threshold advantage as well. So roughly an order of magnitude improvement from our IRIS satellite when we get down to the AV instrument. So those are the two main things. Of course, there's a bit of a cost. With the satellite, one of the great advantages is obviously you can image the globe multiple times a day all over the world. With an airborne platform, you do have to deploy to the region that you want to fly and then cover that region. And certainly there's the aircraft cost itself. But like you said, it's that idea of kind of the fact that these two things could work together. You could have satellite monitoring on a weekly basis, maybe fly the plane a couple of times a year or every quarter, whatever the customer needs are. And the combination of those two views of the ground and the benefits that each of them bring really sort of puts this together as a neat system that can help operators meet their monitoring and detection needs.
Yeah, well, I mean, it sounds like a really great stereo view of things, certainly. I mean, just having those perspectives is so valuable. So give us an example, of measuring with a controlled release then.
Right. Yeah. So controlled releases are really important. So this is where you would have someone on the ground who is at a known location, releasing some methane or compressed natural gas is typically what's used, and then you fly over with the plane or with the satellite, and so then you have a known location with a known measured ground rate, and then you can use you can use that information to validate and verify what's going on with your aircraft sensor or even with your satellite as well. And so we definitely want, as we commission these new technologies, the new airborne instrument, the new satellites, we definitely want to build into our plan these opportunities to release a little bit of gas to help us with that validation, which gives us the confidence then to go out and when we measure something out there in the world where we don't have any information about the ground control, then because we've gone through that process, we can have a good idea of our system is performing. And so when we make a measurement, it's trustworthy and reliable. So yeah, so what that looks like as far as from the airplane perspective, one of my colleagues, Hanford, he'd be typically on the ground working with one of our partners to have a trailer with a lot of natural gas in it with appropriate flow meters and controllers and the piping and the stack and all that. And then, yeah, we're in communication as the plane's coming in, and we would do multiple passes, varying the rate of emission, perhaps varying the angle or the heading that the plane's flying at, and yeah, just building up a good set of data to get that assessment of our system. And it's the same with the satellite as well. So, we would know when the satellite is overpassing that location and get everything timed correctly to have the release and a plume ready to go, so it's imaged by the satellite. And we've even done a couple of times where we've had both the satellite and the aircraft there at the same time, sort of coordinating, that double picture and coupling it with the ground control as well. So putting it all together into a little experimental campaign.
Well, it's so interesting, but I guess it begs the question of how does this compare with other approaches? How are other companies currently tracking emissions, and what are their methods, and what are the advantages and the disadvantages of the way that they're doing it?
Yeah, of course. So most of speaking specifically of oil and gas infrastructure, there's obviously a lot of emissions regulations governing those types of operations, and methane regulations in a lot of jurisdictions in North America and around the world. And the standard ways that those types of missions are being monitored is sort of on-site ground-based measurements, where you would have a team of people coming. They might have an optical gas imaging camera to sort of get a picture of the infrastructure, looking for any releases of methane. Another way is with a little a sniffer, basically. So you'd hold it up and you'd be sampling the air, looking for the methane molecules. So those two are kind of the main ways that are out there to both detect and to quantify emissions from a site. What's great is you're right there at the infrastructure that could be leaking, so you can find those small leaks. But it does take time. You have to go all the way around and look at it, and you have to go site to site to site. And so there's a lot of travel, a lot of costs associated with that, some health and safety with having crews on the roads in these remote locations. So that's where we see kind of some of these alternative technologies as being a real advantage, especially GHGSat's approach with the satellite and the airborne. These are remotely sensed approaches. We don't need to have any presence on the ground. With the satellite, you can view anywhere in the world. With the airborne, you get the plane out to the location where you're interested and you fly over, and there's no direct site access. And you can cover a lot of facilities in one campaign in the airplane. So that idea is that, you can get a lot more coverage. You can look for those big leaks, especially from the satellite, can find the biggest ones, have that kind of routine monitoring. Combine that with the aircraft to perhaps catch those next level of emissions that the satellite didn't see, but the airplane can see. And with that, what you're really doing is you're finding, obviously if the problem is to reduce emissions, you got to find those big ones. and address those first. So you can really give our customer base actionable insight to find those, find those big emissions, and then they can take the appropriate steps, whether that's following it up with ground teams to, find the exact flange or the exact seal that's leaking and make the correction, or even if we're coupling in with some of their ongoing monitoring campaigns, again, they could go to the sites that are known to be leaking because they've been kind of screened and assessed through these remote technologies.
So, I mean, of course, you mentioned the customers, and it's all about the data, so tell us, how are you guys making it easier for people to access the information that these incredible tools are generating?
Yeah, definitely. That's another area. Obviously, if the information isn't easily accessible and available, and then some of that insights just doesn't get communicated on, and the end results don't happen. So definitely, we're making efforts on our analytics side and in our sort of customer-facing interface to have portals and dashboards available to our customers. So as data is coming in, it's being processed and uploaded, and then it's available for them to access and interact with using a GIS layer, and it can sync in with some of their perhaps some of their internal systems that they're using to monitor their operations. So definitely kind of getting towards that level of making it as easy as possible, and certainly timely. We've got to get those results down from the satellite right away. We got to get our data turned around as quick as possible. So we're continuing to improve on just our turnaround times to get that imagery and data processed right away, so that if there is any emissions detected, we can alert them right away, so they can take the steps necessary to mitigate it as soon as possible.
Wow. It sounds like you can really pack it in on the day when the conditions are right. But I suppose it's not just about what you're doing right now, but it's also about what's next. I mean, I think anyone who's tuned into the GHGcast before knows that you guys always have something in the pipeline. So what's next for aircraft emission monitoring over there?
Yeah, definitely. It's been really exciting just to see how from last December to now, we've gone from our first light flight to going through some of these controlled releases, validating the system, getting actual various partner projects and commercial projects flowing. And so it's been really exciting, and definitely 2021 is going to see us continue to progress on the airborne side of things. We have a second airborne instrument that's currently in the works, and we expect to receive that later in 2021. So we'll basically have two instruments now that can service our customers and different regions, starting in North America, but then potentially around the world as well. So definitely on that side of things, we'll have a second instrument to do it. We're basing the airborne instrument out of our Calgary office, which is where I'm at, and so we definitely need to bring on some more people here to support that over the year, not only on the airborne operations side, but perhaps in some of the other teams of GHGSat having some more presence here in the Calgary office. So in the next few months, we're probably going to be going back to the US for another campaign down there with the system, and then gearing up to have that system come back into Canada and do some more flying around Western Canada in through the summer.
So, we're just talking a little bit about process, and just what is a normal day like? What sort of things have you actually flown over?
Yeah, so a normal day, every day can have its own uniquenesses and challenges, but from an aircraft perspective, obviously, typically you would deploy to a region. Maybe it's a shale basin in the US, or, we've done work in the US and we've done work up in Canada in sort of Alberta, BC areas. So you'd deploy, you'd have your project area kind of all flight planned, ready to go. And it would be that idea of you'd check the weather. So one of the neat things, and I guess that's another advantage of airborne, is that, if it's cloudy, we can choose not to fly. Whereas the satellite, it's where it is. And, you lose some observations to clouds. So we do have some operational flexibility with the plane to try to choose the most ideal conditions. And so then you would go through if it's a good day to fly, you'd go through your sort of system checks on the ground before you take off, make sure everything's working, get up in the air, fly for several hours, depending on the range of the plane you're using, collect the data, land, do some backups, get that data kind of ready to be processed as soon as possible.
Indeed. Well, I suppose, the best thing we could possibly do is wish you clear and stable skies. And thank you so much for your time, Warren. Fascinating stuff.
Yeah, appreciate it. Thanks so much.
Thank you. This has been a GHGSat Quickcast. We've many more stories to tell, so subscribe to us at GHGSat.com, or where all fine podcasts are found. For more news and updates, follow us on LinkedIn and Twitter at GHGSat. And big thanks to John Mitchell and Lonely Robot for the music.